and a warm welcome to Kandola Network's second podcast in the series, titled Fireside Chats with Industry Stalwarts. And today we have with us Associate Professor Adam Bjorndahl from Carnegie Mellon University. Dr. Adam holds a PhD in mathematics from Cornell University and is currently associate professor with tenure in the philosophy department at Carnegie Mellon University. He works on logic and game decision theory with a focus on mathematical tools for representing and reasoning about knowledge, belief, learning, and communication. There was an excerpt from his website on the kind of research work he does, and it reads as follows. How do people and other systems make choices? How do they ought to? How do they cope with uncertainty and react to new information? What is information and how do agents obtain and reason with it? This is well and truly in line with the core fundamentals of decision-making in blockchain technologies. And we couldn't be more thrilled to discuss these concepts in detail with you, Adam, today. Right, so let's dive straight in. Could you please break down game theory for our audience today? How do we simplify the concept? What are your motivations? And in your opinion, what is its most pertinent applicability in blockchain?
Well, thanks for the introduction and nice to be here. So let me start with what game theory is. So, when people hear game theory, often they think about, video games, but game theory is much broader than that. Game theory is about decision-making and specifically about decision-making in group contexts. So, think of any context where you need to decide what to do and there might be many factors involved. Maybe you're deciding what route to take to work, which roads to take. And in these contexts, the point is that there are other people who are making similar decisions, who are in that same system with you. And the optimal decision for you to make isn't just something that's happening in a vacuum. It depends on what other people decide to do. If everyone decides to take the same route, it's going to get very congested and be very slow, right? So then you think, okay, I should take the other route. But if everyone decides to take the other route, then it's going to be the one that's congested. So in its sort of most basic form, game theory is just about people or systems making decisions in the context of other people or systems making decisions in ways that influence each other. And the whole field is based on that. So it's actually very general. It's been applied to study things like competition for scarce resources or traffic flow, whether it's, commuter traffic or traffic on a network system or something. It's been applied to study market conditions, supply and demand, all sorts of sort of so-called strategic scenarios. And so thinking about game theory in those terms, it's exciting to me because I like to think about decision-making and knowledge and belief, and it gets sort of more complicated and more interesting when you add multiple people into the mix, because your model for the world is already a complicated thing, but when it includes other people, it becomes kind of recursively complicated. I have to think about what are other people thinking about. They might be thinking about what I'm thinking about. It becomes very there's a sort of feedback mechanism there. So that's all fun. And that's why you get this sort of landscape of solution concepts and equilibrium notions in game theory. It's all attempts to sort of mathematically get a grip on this kind of complicated landscape. And lastly, I guess just to connect it very briefly to blockchain, maybe more generally to like distributed computing. This is a context where you have multiple systems. They're taking actions, they're making decisions, they're interacting with each other. It's exactly the kind of situation that game theory is designed to analyze. The only difference is it's set in this modern context where the scale might be much greater and the types of applications in mind may be different from when the foundational concepts of game theory were first being developed.
That was really interesting. I'm already beginning to think about how complex it can get, and then how you need to sort of simplify that and really arrive at very predictable models as a result.
Right.
So that's really interesting. And very specifically in the blockchain landscape, considering it's very quickly and rapidly becoming, a $10 trillion industry, the market scope is unlimited, and its adoption you can see the likes of big banks. Obviously, it's proliferous in the decentralized finance world, and you can see just as of today, JP Morgan really adopting blockchain technology is more mainstream in its financial transaction landscape, right? Its fundamentals are rooted in consensus algorithms and incentivization behaviors. So what kind of an effect do you think, or a knock-on effect, especially considering how large this is becoming, what kind of an effect do you think this will have on game theorists like yourselves to sort of model human reasoning that will help build networks that soon will not require too much of oversight and have positive outcomes repeatedly? So what do you what do you think? How do you think that landscape is going to really change?
Yeah, so that's a big question, and obviously an important question for the modern world. I mean, speaking from my own perspective, I didn't come to game theory from the perspective of distributed computing or blockchain, right? So I was sort of schooled on more classical examples and learned the sort of equilibrium concepts and so on that anyone learns when they're first learning about game theory. And like I said before, these are all broadly applicable in the context of distributed computing and consensus algorithms. And you talked about incentives. Of course, game theorists have been concerned with incentives, from the beginning. That's part of what is being studied, game theory and decision theory. Part of the difference, maybe though, is scale. And by scale, I mean not just the fact that, of course, in some of these consensus algorithms, you may have, huge numbers of players, so to speak. In game theory, that individual agents are called players, but also scale in other dimensions too. So, when you study a lot of games, a lot of classic games, they're limited in many respects. One respect would be like the set of actions available to each player is limited. There might only be a few actions. You study, like you said before, in a simplified context, you want idealized settings where you can get mathematical tractability. But when you're looking at a consensus algorithm and you're worried about, for example, Byzantine agents, or I should say agents who might be in some sense subverting the overall algorithm, then part of the question on the table is exactly what might they do, right? We don't come to the situation with a preset list of actions that we can kind of study as such. There's a broader question there of what are the actions? Who are the players? This is another departure from a lot of the classical models. It might not be a fixed set of players who are playing. The players might be changing round by round, right? Some might enter and then leave. This is also very different from a lot of the classical models. So it's not that game theory can't handle these types of extensions, but of course, each time you change the sort of nature of the game in this way, you try to expand it and make it more applicable, it creates a lot of interesting new challenges and opportunities for extending the existing theory.
Correct. Right. How do you, diving into your brain a little bit, how do you increase those predictabilities?
Well, so, I mean, if you're a game theorist and you're doing theory rather than, for example, simulation, then tractability is really a key aspect of what you're trying to build. You want to build models which are simple enough that you can actually analyze them, that you can actually prove stuff about them, but not so simple that they're completely detached from the reality that you're trying to capture. So part of the challenge there for the modeler is to develop models, which of course are not going to be perfect. You're never going to have a perfect model which perfectly matches the world, but to develop models which capture sort of sufficiently much of the structure of the situation that you want to study so that what you prove about it has real world applicability. And that's part of the challenge. And it's interestingly, not a purely mathematical challenge. Like developing the right model isn't a theorem that you prove. It's more like making the right definitions. And that's that's a sort of, in some senses, more of an art than a science.
Adam, on that note, so if one is building a Web3 protocol that is supposed to serve, say, a decentralized finance application or simply a decentralized data exchange application, given that the nodes who make up this whole network are all independent nodes who have agreed to apply a protocol, how do we balance the rewards and penalties? rewards for doing the task that the platform expects you to do, and penalties if you fail to. How do we draw a balance?
Yeah, that's another very sort of broad and big question, of course, very pertinent. And actually, it leads to maybe another example. I was talking about scale as a way of sort of, pointing out how applications in consensus algorithms and blockchain depart from more classical applications. Another dimension of that is what's called in game theory the utility function, right? This is like the mathematical representation of what the individual players want, what they prefer, what their goals are, right? In classical, examples of games, the utility function is just specified. I tell you what it is. I write it down. There it is. If you go into this world and you want to say, well, I want to study the game theory of this consensus protocol, right? And in addition to what I said before, having to specify who are the players and, what actions can they take, you also have to have a mathematical specification of what they want. And that's also highly non-trivial and interfaces directly with your question about incentives versus penalties. A prior question to that is to establish what do the players actually want? And they may not all want the same things. Some of them may want to, play their part in this sort of distributed protocol. They're sort of like good citizens in this sense. Some of them may want to extract as much value in terms of incentive or monetary payoffs as they can from the system while putting the least amount of work into it. That's a standard sort of selfish kind of player. Some of them may not be interested in extracting value at all per se. They may be interested in disrupting the operation of the system, right? They're not there to get value. They're there to make sure the system doesn't work very well or that it works in an unexpected way. So in order to answer this question of how to balance incentives versus penalties, first there's this kind of prior question of even establishing a representation of what are the preferences and desires of the various agents involved in the system and how do we represent those?
So would the threat of getting ejected from a network, would that be a deterrent enough for the players?
Well, I mean, it depends on what your preferences are. If your goal was to skim value off the system, then being ejected puts a stop to that goal. Then yeah, that's a kind of you want to avoid that at all costs, right? But there are other goals you might have. If your goal was to disrupt the system, it depends. If you want to disrupt it continuously, being ejected is a problem. If you want to disrupt it as a one-shot deal, then being ejected maybe isn't so much of a problem. It doesn't matter what happens to you after you've succeeded in the disruption.
Correct.
There's also a question of I mentioned before, players may come and go. If you take the perspective that you're one player, you've got this one shot, then being ejected might be a harsh penalty. But if in some sense, you're an agent who controls multiple players who can join and leave the network, then having some of them ejected might not be a big problem if you can always get new players in. So again, all of these questions interface. We're in some sense, like new lands here, looking at the interaction between shifting pools of players, indeterminate sets of actions, and sometimes wildly different preference structures.
Yeah. So I came across two interesting theories in your space, and one was Nash's equilibrium, and the other was prisoner's dilemma. How do we apply these tools in studying Web3 protocol?
Okay, well, let me start with prisoner's dilemma, because that's a really popular thing to talk about whenever you're talking to a game theorist. So prisoner's dilemma is this, for people who haven't heard of it before, it's this sort of simple scenario where you've got, you can tell different stories about it. The classic story is that you've got two prisoners who've been captured for committing a crime, and they're sort of separately given the chance to rat the other person out, right? So they can rat the other person out, and if they do that, they get a lighter sentence and the other person gets a harsh sentence, unless they both rat each other out, and then they both get, harsh sentences. So essentially you set up this game where you have there's two players and each player has two actions. They can take a cooperative action, which is kind of like staying silent, or they can take this, what's called a defecting action, which is like stabbing their opponent or their partner in the back. And it's set up so that, in some sense, the best result overall for the group, for the two players together, is for them both to stay silent, because then there's a limit to how much they can be punished. But from an individual perspective, if your opponent is going to stay silent and you rat them out, well, you get the benefit of whatever deal they offered you to try to incentivize you to rat them out. So you have this kind of local incentive to rat out your opponent. But they have that incentive too. And so in the end, since you're both kind of following your own selfish motivation, you both rat each other out, and you're both worse off than you would have been if you had both stayed silent. So that's the prisoner's dilemma in a nutshell. And you see there are lots of sort of games in game theory that have similar kind of structure, where there's some kind of tragedy, in a sense, where in virtue of everyone pursuing what's best for them individually, the group suffers. Actually, an even more, in my opinion, even more interesting example of this, called Braess's paradox, which is a network flow game. So again, think of like choosing the route that you want to take to work. I actually start my game theory class by going through this game with the class. I won't go through it in detail, but the basic idea is you set up an initial situation, everyone chooses the route they want to take to work, and they sort of distribute themselves across the network in a nice equilibrium way, right? Everyone takes about, on average, say 30 minutes to get to work. But then you change the network. This is where the paradox comes in. You change the network by adding a new route to it. You add a new road. It's like you open a new road. A road that was closed before becomes open. And you would think that would make things better. But in some network structures, adding that new road actually makes things worse. And to be clear, it's not that it makes things worse for some people and better for some people. It makes things worse for everyone. Literally every person now has a longer travel time, and all you've done is given them more choices. So it's called a paradox, not because it's false, it's a true result. It's because it's so counterintuitive that having more choices in the context of everyone sort of individually pursuing their own interest is not guaranteed to produce the overall best result. It can actually produce a worse result for everyone. So these types of games, sort of to bring it back to your question, how are they applicable? Well, you can take kind of two views. On the one hand, you could say, well, they're not applicable because they're highly idealized. I mean, we never encounter true prisoner's dilemmas in life because our incentives are, mixed up with many different things. We don't just care about jail time. We also care about things like how we treat our friends and reputation effects and the fact that we might play the game again at some point, blah, blah, blah. Same with Braess's paradox. You can say there's too many idealizations. But this gets back to the core of what I was talking about. Every game has idealizations. But what you can learn from them is, for example, in Braess's paradox, what you learn is that something you might not have expected before, which is that it's possible to increase everyone's choice set and make everyone worse off. So in some sense, it doesn't matter if that particular game doesn't model actual traffic flow in some specific city or whatever. As a theoretical tool, it's telling you what's possible and what's not. And that paradox is telling you it's possible to that individual selfish behavior actually makes the group worse off.
Very interesting. Very, very interesting.
I'm finding it extremely interesting as well. And I just had a follow-on question, in fact, alluding to exactly what you were mentioning earlier. What are your everyday examples of like a prisoner's dilemma that you most commonly see, especially coming from someone who really studies human nature and human behavior philosophies? Can you share with us some of the most prominent examples in everyday life that makes us really face these decisions, and what sort of ideal state those could be?
Well, so I want to emphasize again that in some sense, no situation that you ever face is a true prisoner's dilemma, because it's such an idealized setting. It idealizes away from all sorts of other ways that you might care about the world. Like maybe you care about the other person, or you're worried about the reputation that you might gain because other people watch you, behaving badly or something. But the core of the insight there is, I guess, maybe not prisoner's dilemma per se, but something a bit more general, is that there are contexts where you have these local incentives to make a choice which is better for you either in the short term or locally, in the sense that it's better for you even though it's worse for other people. And that's sort of traded off against the kinds of considerations that might incentivize cooperation, like these things that I mentioned, reputation effects, or even just very commonly in prisoner's dilemma, people talk about, well, what about repeated prisoner's dilemma? If you're going to play again and again with the same person, then you do have an incentive to cooperate because they'll punish you later if you defect on them now. So any situation where there's this tension between sort of like the group good and your individual sort of local selfish incentive is, I don't want to say a prisoner's dilemma because formally it might not be exactly that, but it's the type of situation that game theorists have been interested in modeling with various different kinds of games and tools. So let's see, you want like a real world example. I mean, I just think about any time I'm tempted to do something like maybe I'm driving my kids to school in the morning and, oh, it's a good example. The school has asked us not to park on the street right in front of the school, because if all the parents park there, it would be a crazy traffic jam, and it would just
like the exact same thing. Yeah. Sorry, continue. Yeah,
exactly. And so, most of us dutifully go and park on some side street and walk a couple of blocks to get to the school. But every day you see like there's some parents who decided like, well, I can park on the street today. And it's like there's a sense in which, that's better for you. You save the time and that you have the convenience of that. But if we all did that, it would be a disaster. And so, you're sort of relying on other people to make the choice which is worse for them in order to enable you to make that choice. So I'm not saying that is a prisoner's dilemma. I'm saying that that's the kind of trade-off that you see a lot in these games between individual versus common good.
Okay. All right. Adam, sorry, quickly before we move on, I want to throw light back on Nash's equilibrium and how that sort of plays its part in Web3 modeling, considering it's very different from prisoner's dilemma in the sense that, the decision-making and interaction is more, combining strategies to work towards an ideal state, and having the ability to sort of really discuss and collaborate in this case, right? What are your thoughts on that?
Yeah, I'm glad you brought that up, because you're right. I didn't come back to the second part of Nara's question about Nash equilibrium. So I think the first thing to be really clear on is that prisoner's dilemma and Nash equilibrium aren't the same type of things in game theory. Prisoner's dilemma is an example of a sort of idealized like game where you've said there's these players and they have these actions and they have these preferences, and then let's look at how the theory predicts that they'll interact with each other, and let's draw some insights from that. Nash equilibrium isn't a game. Nash equilibrium is a tool for analyzing games, which is to say, when you give me any game, and then I can say, well, I'm going to try to find the Nash equilibrium, which you can think of as a kind of like stable point of play where, the Nash equilibrium is sort of saying, if all the players were behaving this way in the game, then none of them would individually have an incentive to behave in any other different way.
Correct.
So it's this idealized like point of play. So it's not a game. It's like a point of play in an arbitrary game, which is somehow stable in some sense. And Nash equilibrium is by far the most like common and cited and used solution concept in game theory, but it's not the only one. And especially in the context that we've been talking about in this podcast, right? Talking about distributed protocols and consensus algorithms and so on. I think there's a very good case to be made that Nash equilibrium is probably not the right tool for analyzing these kinds of games. Nash equilibrium was, invented by John Nash. I want to say in the 50s, but I'm very bad at dates, so someone can fact check me on that. But it was invented at a time when we didn't have the mathematical tools readily available to sort of properly represent interacting hierarchies of beliefs, right? Like, what do I think that you think? What do I think that you think that Nara thinks, and so on. Those tools were sort of in their infancy. And Nash equilibrium gets around those representations exactly by making this strong assumption that says everyone is sort of has, in some sense, perfect information about what everyone else is going to do, at least probabilistically speaking. And then let's try to find a stable point in that configuration.
Correct.
But if you probe a little bit at those assumptions, you realize that many of them are not necessarily applicable in the kinds of situations that we're looking at. So let me just take one example of that, a very simple example. The probabilistic beliefs that you're supposed to have in Nash equilibrium are independent from player to player. That means that my beliefs, say we're in a 3-player game, right? My beliefs about what you might do, Kriti, and my beliefs about what you might do, Nara, they might be probabilistic, but they're independent. Nash equilibrium assumes, it demands that each player treats their opponents as independently randomizing or in some fixed way, right? But if we're in some kind of distributed protocol, I should be taking into account the fact that some of my opponents might be colluding, and therefore their actions might be correlated with each other. Nash equilibrium just prevents me from taking that into account. It just, right? We can weaken that assumption and it becomes something called correlated equilibrium. And we get a sort of weaker, more general solution concept, which includes now players who can consider the possibility that the actions of their opponents might be correlated probabilistically with each other. And that's just one example of changing the underlying mechanics to try to get a tool which better suits the kinds of situations and the kinds of notions of stability that might be at play.
Very interesting. We want to be able to use these tools to study our protocols for the decentralized platform that we are building. So I think these pointers are going to be very helpful.
Absolutely. Absolutely. I think at this juncture, I really want to throw a little bit of light on Kandola network. And as you know, at Kandola, we're building a decentralized data exchange platform that has direct implications in backbone communications and compute for domains like IoT, enterprise communications, social fi, healthcare, and a whole lot of other industries, so to speak. Our consensus algorithm, PORT, is designed to handle incredibly atomic and deterministic operations, enable massive gains in TPS and scale without incurring any network costs. That's one of our main USPs. And it ensures data security, data integrity, data authenticity by using cryptographic primitives. That's our core vision, and that's what we're really setting out to build and deploy. So thank you, first of all, for being one of our primary academia peer reviewers of PORT. We've really valued your contributions thus far. Can you tell our audience a little bit about the problem that you're really helping Kandola solve? What has your approach been? What has the process been so far? How it is that you've gone about implementing it, or any other thoughts that you'd like to share?
Yeah, sure. So it's been really fun for me to get to know this project because if it hasn't been obvious from the previous discussion, I'm like a theory person. Like that's my background. I do like the theory side of things. And this has been a chance for me to get a sort of, firsthand view into some direct applications and be a part of the kind of crucial linking between theory and applications that needs to take place to have sort of confidence that the tools that are being built will actually work the way that you want them to work. And that's a difficult problem. And that's what I've sort of been engaged with in working with Kandola network and working on the PORT protocol has been sort of trying to develop models, whether they're game theoretic models or other types of knowledge representation models, to capture aspects of the underlying protocol and thereby use those models to try to prove, at least in some idealized but still hopefully applicable contexts, that those protocols are successful in what they're aiming to do, both in the sort of end result they're aiming to achieve, but also maybe more importantly, or not importantly, but more to the point, that they're resilient against the kinds of attacks or crash failures or what have you that might potentially impact them and reduce the sort of value of the overall protocol.
Very nice. And Adam, as you're aware, one of the tools that our team came up with in building the PORT protocol is a batch derivative, which takes in the original batch of messages and inserts messages that are faulty, that are not compliant to the platform, and challenges other nodes of the network to identify where they exist. So once nodes perform the task, then it is evidence enough that they've done the work. Now, the batch derivative propagation across the network, that also plays a very important role. And you've done analysis on how a batch derivative propagation tree is collision resistant. If you can share some light on your findings for our viewers.
Yeah, sure. So first, let me just say the batch derivative propagation protocol that's part of the general port protocol. The basic idea behind that is really intuitive, right? It's that we want a bunch of different systems to verify something, but if they're all verifying the same thing, that just throws wide open the doors for collusion and for many of the nodes of that network not really doing the work because it's already been done before and they can kind of just copy it. Or you could have one player who's controlling multiple nodes and does the work once and makes it look like in the system they've done the work, 100 or 1,000 or 1,000,000 times, who knows? So the batch derivative idea is to say, well, look, what we're going to do is we're going to, rather than everyone verifying the exact same thing, as you said, we're going to insert sort of bad bits or faulty messages or fake parts, which slightly change the object that's being verified in a way so that each verification that's being performed is slightly different than each other one. And that allows, that sort of slams those doors shut. Now you can't just copy your peers because they're actually verifying something slightly different, right? Of course, part of the importance of the algorithm is to sort of stitching all of those slightly different verifications together into the final product, which is the verification of the original thing you wanted to verify. And that's all sort of taken care of by the algorithm. But the protocol itself, while it's collusion resistant, it doesn't completely close that door, without a crack to collusion, because each time, each node which is verifying, some slightly different batch derivative. Well, you ask, how might it be slightly different? The difference is introduced by some other node. If that other node that introduced that difference is colluding with the node that gets it, then there is now again the possibility of sort of copying. It's slightly more complicated, but now it's like, say, Nara, you passed me a message which is slightly different from the one that you verified, but you tell me how it's different. So you cheat by telling me how it's different. If you were to do that, then I could just put together this piece of information, how is it different with your verification, and sort of get a verification that wasn't really independently arrived at. And if this happens at scale, then you have something similar to the same problem you had before. What prevents that, in theory, from happening at scale is the network structure, that, it needs to be the case that the person who's passing me the batch that I'm supposed to verify is someone I'm colluding with. And unless the network is full of colluders, like high percentage of colluders all working together, the idea is that that's going to be very unlikely. That the chance that the message that the message is being passed to me by someone who is willing to cheat with me will be very low. So the analysis that I've been working on, sort of in its early stages right now, is basically looking at various network structures, right? Like tree structures, for example, that's what's on the table right now, and analyzing what is the sort of expected amount of collusion that would be possible given a certain raw proportion of colluders, so that we can sort of put an upper bound on how much collusion we can expect that's a function of how many colluders there actually are.
Wonderful. I, in fact, look forward for your full analysis, and like we've discussed, we want to be able to publish this in an IEEE conference and share the findings with our viewers.
Yeah, that's what we're working towards.
And Adam, quick question from my end. Having gone through Kandola's port protocol and sort of really dived into it in detail, you see a lot of scope and applicability, and we're really glad that you see that potential as well. What milestones do you think Kandola Network should really be looking at crossing in the coming months in the space?
So I'm going to answer from the theory perspective because that's where my expertise lies. I'm going to leave the sort of engineering milestones to the experts on that. But from the theory perspective, what you see a lot of times when you read the kind of like white papers and the blog posts or the whatever, people are putting out these ideas for different distributed protocols. You see these ideas, you see these possibilities, you see these like sort of hopeful guesses that this algorithm is going to do this, it's going to be resistant to this, it's going to establish this and have this throughput and have this efficiency and so on and so on. But what you don't see a lot of is the sort of theoretical proofs to back it up. And so the milestones that I am hoping to sort of work towards here in conjunction with you all is actually establishing some of that theoretical underpinning to the sort of promissory notes and simulations and implementations that of course are all themselves very important, but the theoretical foundation sort of raises this this project to a new level. It puts it on a different kind of foundation than many of its peers. So that's the kind of milestone that I would want to see. I would want to see models for fragments of how this algorithm works together with proofs of correctness in those contexts, because that gives us more certainty that the system that we're designing actually has the resiliencies that it was designed to have and that we hope that it has.
Fantastic. Very exciting.
Fantastic. Adam, your thoughts are excellent, and this is the kind of input that we at Kandola would need, and we are very glad to found you in and had this opportunity to link with you, connect with you, and work with you. I want to add that we are working on a revised port protocol where a few key changes have been made to how our Bash derivative tree propagates. From being a binary tree, now it's going to be a dynamic tree, and every node of the network will have the opportunity to identify a specific role that they'll play in the process. Are they going to be a Bash derivative verifier, or are they going to be a Bash derivative propagator, or are they going to be an audit node? So it's a lot more complex a protocol, and we are working on that specifically to tackle adaptive attacks. You had mentioned about that in the review. So those are all the new changes that are coming in, and we'd like to again share the updated protocol with you and get your thoughts on that, and publish it to the outside world. This was a fantastic podcast, and thank you so much for being available to speak to us and sharing your expert opinion on game theory and Web3 applications.
Yeah, absolutely. Thank you so much for having me.
Wonderful. Thank you. Thanks so much.
Thanks.
Bye.